Hi everyone, this is a super exciting lesson because it is about the most important theorem in calculus, arguably one of the most important theorems in math, which is the fundamental theorem of calculus. And I affectionately call this FTOC, fundamental theorem of calculus, and there's kind of two parts to the theorem, hence the FTOC 1 and FTOC 2. Okay, so what is this all about? Well, we're going to start by taking the idea of an area, but we're going to create an area function. We're used to thinking about area as a number. We need to get used to thinking about now an area function. So what do I mean? Well, if you have a graph of f, as we do here, an area function can be made by just writing a definite integral. Here's my definite integral. And the integral is going from some number, in this case 0, to x on the top, right? And then I have the function here inside. So what that means is I'm starting my area calculation here at x is equal to 0, and then I'm going out until whatever number is at the top of the integral. So if I am doing a of 0, then that just simply means I'm doing the integral from 0 to 0, and we know that if you don't go anywhere, you cannot accumulate any area, so that integral is 0. If I'm doing a of 2, then I mean the definite integral from 0 to 2 of f of t dt, which of course means the area between f and the x-axis going from 0 to 2. And since you can see that those two triangles, like one is positive, the other one's negative, and they're the exact same area, this is going to be 0. A of 4 would mean we are going, from 0 to 4. So we've got these two triangles that already canceled out. And then we have this area. Remember, integral is always the area between the f and the x-axis. And then I have this last area here. Well, the blue and the red triangle is going to cancel out also. So the total is still going to be 0. So this integral is equal to 0. And now, then when I say a of 6, I'm going to 6, from 0 to 6, f of t dt. And by the way, the reason we're calling this t in here and not x is because now x has this new meaning of how far. How far am I calculating area? So I can't use the same letter inside the integral. Anyway, this integral, well, I know that from 0 to 4, I basically got no area. So now from 4 to 6, it's just the area of this little trapezoid here, this trapezoid, this green trapezoid. And that green trapezoid will be 1/2, that's trapezoid formula 1/2 of B1. B1 is 1 and B2 is 3. So 1 plus 3 times the height here is 2. So this is going to be 4. Okay. Now if you're asked to do something like a of 7 and it's an estimate, the reason it's an estimate is because this right here is a curved, it's a curve, and you don't know the exact curve equation. So you cannot do something fancy like a Riemann sum, but you can certainly do just a triangle and say, well, it's going to be, close to this triangle. It's a bit over that, but that curved part, really the exact curved part that we're after is this whole thing, right? That would be, so area from 0 to 7 would be all that stuff plus this blue curved piece, right? But if I cannot calculate that, I can certainly estimate it as a triangle of base 1 and height 3. So the integral from 0 to 7, or a of 7, will be all of the stuff I already accumulated, which is the integral from 0 to 6, plus the the triangle, which is 1/2 of 3. So we could say that this is going to be approximately 5.5. I'm sorry. Okay, so that's the idea there. Okay, so now that we have this new concept of an area function, and notice we could write it as a function because we have the definite integral as a new tool. So we can write this area function, which is the area starting at A and ending at X under the graph or between the graph of F and the x-axis, right? If the theorem says f of x is continuous on AB, then this area function will also be continuous on AB, and it will be differentiable on AB. And this is the big drum roll, the derivative of that area function will just be f of x, okay? In other words, the area function is the antiderivative of f of x. So let me see if I can give you an informal proof of why that's true, right? Okay, so let's imagine a function f of x and say, we are going from A to B. I'm imagining a continuous function because that was the condition of the proof of the theorem. And so basically I'm going to define my area function as the integral from A to x of f of x dx. This right here is f. So I'm starting my area at A, and then I'm going to calculate that out until some x, which is say here, and say that this area that I just wrote is obviously going to be this shaded thing. Okay, this is the area from A to x, little a to x. Okay. Now, so let's write that down. This is the area from A to x. Okay. Now I can do the area of x plus h, right? So I'm starting still at little a, but now I'm going out a little bit further to x plus h, and this is therefore the area from A to x plus h. So h is just a little bit over. It's assumed to be a little positive number, though it probably doesn't have to be. And I'm calculating now until there, right? So I'm now calculating this blue area. All of that is A of x plus h. Okay. So if I do this and I then subtract, so if I subtract, I want to subtract A of x from A of x plus h. So if I do A of x plus h minus A of x, I would have the second integral minus the first integral. And this would represent this area here, this green shaded area, or maybe I want to make it something brighter, maybe this yellow shaded area, right? This sliver, because this first integral represents all the way to h. The second integral represents just to x. So then the subtraction, the difference, is going to represent the area in between x and h. Okay. So now I can take these two equations on both sides and divide them by h, okay, just algebra. And I'm now going to take the limit of each of these as h goes to 0, okay? So I'm going to take the limit of both sides as h goes to 0. Okay, so now if we look at this, then on the left side of this equation, the blue box is nothing other than our old friend a prime, right? This is the derivative of the area function, a prime of x. And on the right, let's take a look at what we have. Well, this yellow piece right here, let me just color this correctly. This yellow piece right here without the limit, the thing on the top here, is, we said, this area, right? It means the area in between that yellow area on the graph, right? And you can see that that yellow area, as h goes to 0, which is what is happening, right? As h goes to 0, this yellow area is going to become more and more like a rectangle. So as h goes to 0, it's more and more like a rectangle that has a width of h and a height which gets closer and closer to just f of x, right? And let me explain that a little bit. If you think of an h which is, kind of wide, then on one end you have a y that's f of x, and on the other end you have a y that's f of x plus h. But if the width of the rectangle is getting smaller and smaller and smaller, you can see that the height becomes closer and closer to just f of x, right? So this whole yellow thing on the right here is looking, as the limit is happening, right? This whole top here looks more and more like f of x times h, and the bottom is h, right? So in other words, the h's can cancel, and since f of x doesn't depend on h, the final answer here is just f of x, right? So that's the theorem. It's saying that a prime of x, the derivative of the area function, is equal to the function under which we're calculating the area, right? A prime of x is equal to f of x. So why is this such a big deal? It's because we now know that when you're thinking of your ladder and you're thinking of any f on this ladder, the daddy or the mommy on top of little f is its own area function, right? So the area function is equal to the antiderivative, because we know that on top of little f, what we have on the ladder is its antiderivative. Well, its antiderivative happens to be its area function as well. Okay, that's the big deal. Informally, this means that if we make an area function using f of x and then take the derivative of the resulting area function, right? So take the derivative of a of x, we get back the original little f. And this is why we say that integration and differentiation are inverse operations. We see that up in this equation right here, we said already that a prime of x right here is equal to f of x, but we can also write it this way. Here is a of x, and I get a of x by taking little f and then doing an integral. But if I then follow that up with a derivative, then I'm just back to the function that I started with. So the derivative and the integral are inverse operations. They undo each other in that sense. Becomes more and more. Okay, what do problems look like around this concept? Well, there's a few different types. The first one is emphasizing this idea that the derivative and the integral are inverse operations. So here we see d dx of an integral. This integral right here is an area integral. You can see that. It's an a of x. It's the area under the cosine graph starting at -5 and going until x. So you're going to, if you take the derivative of that, differentiation and integration are inverse operations, and your answer is just going to be the cosine function, and you're going to replace this t back with x because there's no longer a need to say cosine t. The reason we say cosine t here is because we have to say x up there, but in our final answer, we just are going to say cosine of x. This one, again, doing the same thing. This is our function. This guy is an area function. If I take a derivative of the area function, I'm going to get the integrand back, right? So this is equal to 1 over 1 plus x squared. This right here is the same thing in different packaging. Big f of x is an area function, and we're asked to find big F prime, right? So if we're finding big F prime, this is literally, the fundamental theorem just that we went over just says that if this is little f, right, then big F prime of x is going to become this function. So it's just the square root of 1 plus x squared, right? So once again, like just putting the x in there is how students sometimes remember this. And then big F prime of 1 means if big F prime of x is this, big F prime of 1 is 1 plus 1 squared, or the square root of 2. Okay, now, sometimes the area functions are a little more complicated where you have something on the top which is not just x, right? So for that, what we're going to think is this is really a composite area function, okay? It's really like saying we're taking the derivative. It's an area function, but it's a of x squared, right? So we're going to use the chain rule, right? And in the chain rule, the inside function is the x squared and the outside function is the area. So we want to do out prime of in, right? times in prime, okay? So the out prime, we know the derivative of the area function is this. So we'll just do sine, and then we have to put in x squared. We have to put this in for t, right? So I'll get sine x squared over 1 plus x squared squared times the in prime is 2x. So this is going to be 2x sine x squared over 1 plus x to the 4th. Okay, this guy, same sort of idea, composite area function. So this is like saying a of t to the 4th, right? So the a prime is going to be this thing, right? That's the out prime. And then the in prime is going to be 4t cubed, right? So out prime of in is going to be, this is in, this is the in. Out prime of in, we just first put that into the function, right, times the in prime. So you'll get 4t cubed times the square root of t to the 4th, which I think we can simplify to 4t to the 5th. Over here, same idea, right? So this is going to become secant squared of tan theta. That's the out prime of in. That's the, first piece of the chain rule, and the second piece will be the derivative of that, which is secant squared theta, right? So this is f prime of theta. And you cannot make that secant cube because this is tan theta and this is theta, or secant to the 4th because it's tan theta and theta. So you cannot combine that further. Something like this. These are problems that use the properties of the definite integrals along with area functions, right? So if you have the derivative of this looks like an area function except the number is on the top, right? So we're going to use the properties of integrals to say we know that this is equal to minus d dx of the number on the bottom, right? That's our reverse property from our last lesson. So once we get it there, then we can just use our fundamental theorem. Over here, same idea. First flip to have the number on the bottom, and then 2 plus t squared, and then chain rule, right? So put that top thing in for a prime of 1 plus 3x squared, and then times the derivative of that, which is 6x. So I think the final answer here is negative 6 over 2 plus 1 plus 3x squared squared. Okay, let's go on, finish these off. This guy, first we want to move the 0 down, so that will introduce a negative sign out front. And then we want to do the chain rule, so negative 1 over 1 plus tangent squared theta times the derivative of tangent, which is secant squared theta. And now this is also secant squared theta, right, by a trig identity. 1 plus tangent squared is equal to secant squared, and so this comes out to be negative 1. So sometimes you can use pre-calc to simplify your answers further, and you will be expected to do that. This guy, let's see, flip it first to get the number on the bottom. Okay, and then I would say this f prime of x will be equal to negative e to the x squared squared times 2x. So negative e to the x to the 4th times 2x. And then f prime of negative 1 means put this negative 1 into this equation, our equation that we just found for f prime, right? So just let me be clear. This is f prime down here. So that's going to be what? It's going to be negative e to the negative 1, the quantity to the 4th, times 2 times negative 1. So I think that's positive 2e to the 1, which is 2e. Okay, are we getting to the end? I'm getting tired. I'm sorry. Okay, this one here. This is different in that there's no number. There's a variable on the bottom and on the top, right? So for these, we're going to use the properties of functions, right, from pre-calc, you might remember odd and even functions, right? Odd functions are like our sine function. That would be an odd function, right? So in other words, sine of pi over 2 is 1 and sine of negative pi over 2 is negative 1, right? So for these odd functions, f of negative x is going to be equal to negative f of x. Even functions are like our cosine function, right? So our cosine function, you can fold it over the y-axis, and f of, say, pi over 3 is going to be the same as f of negative pi. Cosine of pi over 3 is 1/2, and cosine of negative pi over 3 is also 1/2. So f of negative x is equal to f of x, right? So we can use symmetry to do integrals sometimes, right? Because integrals are about area. So I could just look at these and know that, for example, if I integrate my sine function from there to there, right, from negative pi to pi, I'm going to get 0 for my answer. If I integrate my cosine function from, say, here to here, so that would be what, negative pi over 2 to pi over 2, then I can just find like half of that, 0 to pi over 2, and then double that to get my area, right? So this is the kind of idea here. Always look at this integrand and think to yourself, is that even or is it odd? This guy is even, because if I did f of negative t, I would get 1 over 1 plus negative t, the quantity squared, which is the same as the function right there, which is f of t, right? So that's an even function. So this integral will be equal to 2 times the integral from 0 to x squared, just by symmetry. The integral is always an area, right? The definite integral is always an area. So I am just taking my area from 0 to x squared and doubling it. So then I just do what I did before now. Now I put the x squared in, and I get 1 plus x squared squared times 2x. So my final answer will be 4x over 1 plus x to the 4th for that problem. Okay, we are on to the second part of the fundamental theorem, right, which is also super important. In fact, if you're an engineering student, as I was, this is really what you do all the time. So then when I started teaching math, I had to kind of go back and review the first part, which I just told you, right? Because the bread and butter everyday science uses this second part of the theorem so much more often, right? And this is what is so useful in science and engineering. And the way the theorem is stated here is that if little f is continuous at every point in a, b, then the integral of little f from a to b will be equal to big F of b minus big F of a, right? And so big F is the antiderivative. You know that from the ladder, that's how we were usually calling the antiderivative, right? Big F. So to find the area under little f from a to b, you just find the difference between f of b and f of a, right? Big F of b and big F of a. So we're seeing that the area under little f is related to the y value difference between big F on that same interval. Okay, let's take a look at this. This one we already know the answer, right? It should come out to be 1/3. We've calculated that the hard way, right? But let's do it with FTOC2. For FTOC2, this says that I can just find an antiderivative of the integrand, which is x cubed over 3 by the power rule. And then I'm going to, this is notation you need to master. This means take the antiderivative, right? Now it's going to mean take the antiderivative, right? So we've done that. Once you do that, you drop the integral sign and you put this bracket on and you put the numbers on the top and the bottom. And then you're going to do top minus bottom, right? So it's going to be 1 cubed over 3 minus 0 cubed over 3, which is 1/3. Next one, same idea, find the antiderivative first, right? So just doing the power rule, reverse power rule on each of these. So add 1, that becomes t to the 4th, and then divide by the 4, so the 4 goes away. Add 1, that becomes t to the 3rd, and then divide by the 3, divide this 3 out, right, with that 3, so it becomes t cubed over 4. And then here, add 1. Don't be taking a derivative. We need to take an antiderivative, right? So, sorry, let me do that piece again. Add 1, that becomes squared, and we'll cancel that 2. And so this is my antiderivative, right? And now you've done the antiderivative, so you don't write an integral anymore. You write the bracket and the 0 and the 2, and then you put the top number in first, and you get 16/5 minus 8/4 plus 4/5. All of that minus, check the bottom number. Even if this is 0, it may not always be 0, but in this case, it is 0. So answer now is coming out to be 16 plus 4, 20 over 5 minus 8 over 4. I think that's 4 minus 2 or 2. Okay. All right, let's go on to this one. Now, addition, subtraction, right? So you can do the pieces separately. The antiderivative is e to the x plus x cubed over 3. Add 1, divide by 3. Add 1, divide by 2. And then put the bracket on, and this is going to be e squared plus, I'm sorry, what am I doing? Yeah, e squared plus 8/3 plus 4 minus e to the 0 plus 0 plus 0, right? So notice, here's what I mean by make sure you check that bottom even if it's 0, right? So e squared plus 8/3 plus 4 minus 1 is equal to e squared plus 8/3 plus 3. Okay, and we'll leave it like that. You can simplify the number and the fraction if you like. Let's look at this one, right? So here, I'm going to first recognize that this 4 can be thought of like this, 4 times 1 over rad 1 minus x squared dx. And then by the constant rule from last class, the 4 can be pulled out through the integral, right? So then I have this, and now the antiderivative of rad 1 over rad 1 minus x squared is arc sine, right? So we are remembering that sometimes antiderivative is just a matter of remembering the derivative, right? If the derivative of arc sine is that, then the antiderivative of that is arc sine. So that's what I do there, and then I'm going to put my 1/2 on the bottom and my 1 over rad 2 on the top. And remember, 1 over rad 2 is the same thing as rad 2 over 2. So then I'm doing 4 arc sine rad 2 over 2 minus arc sine 1/2. Arc sine rad 2 over 2, we've got to be able to do this without a calculator, guys. This is pi over 4 minus pi over 6. And, you know, you can simplify it further, but we won't. We'll just leave it right there. Okay, what else do we have? Something like this. Be careful not to just do the antiderivative of the top and the bottom, right? That doesn't work. You know from a couple classes ago that you first need to rewrite that integrand like this, and then you're going to continue to rewrite it like this, and then you're going to find the antiderivative, which is ln v plus v cubed, and we're going from 1 to 2. So this is going to become ln 2 plus 8 minus ln 1, which is going to be 0 plus 1. Make sure you put that second piece in parentheses. It's minus all of that evaluated there, right? This is like my f of b minus big F of a. Okay, and so I get ln 2 plus 7, my final answer. Okay, this guy, you have to be careful to not do, again, the antiderivative of this and this. We're going to first have to FOIL that out. U squared minus u minus 6, all of that du. And then do the antiderivative, u cubed over 3 minus u squared over 2 minus 6u from 0 to 1. And then put all the stuff in. So 1/3 minus 1/2 minus 6. All of that minus 0, and then you can simplify that. Okay, here we have for g a piecewise function. So piecewise function, remember you split the integral into these pieces. So this is the integral from -2 to 0 of f of x dx plus the integral from 0 to 2 of f of x dx. We're using the adding intervals property, and we're using these pieces, right? Go use, the rule to see what your pieces should be. So this right here is 2, right? So that's our box property. I mean, you can do it with the box, or you can actually, let's do it with the antiderivative. The antiderivative of 2 is 2x, and we're going from -2 to 0. And then the antiderivative, actually, let me write this out a little differently. I want to make sure you're understanding. So this is equal to, for this first stretch, right, the function rule is 2. So this is -2 to 0, that's the first stretch, 2 dx, plus for the second stretch, the function rule is 4 minus x squared, right? So for the second stretch from 0 to 2, my function rule is 4 minus x squared dx. So that's how you deal with a piecewise integral. And here we would have 4x minus x cubed over 3, 0 to 2. This guy will be 0 minus -4. This guy will be 8 minus 8 third minus 0. So I think we're going to get 8 plus 8 minus 8 thirds, 16 minus 8 thirds is what we're going to get there. Okay, we are almost done. This guy here is about being careful with the assumptions of the FTOC, right? The FTOC fundamental theorem assumed that the function is continuous across the stretch from A to B, right? This function here, 1 over x squared, is it continuous? I would hope you know that it's not. We have a vertical asymptote right there at 0, right? And the function looks like that. So it's not continuous. You're not allowed to use the fundamental theorem. If you do use the fundamental theorem, you're going to get the wrong answer, right? Let's see what happens if we did do just, okay, if I just don't think about it and I just start doing my theorem and I get this, I first rewrite this, and now I'm going to add 1 and divide by that, so I'll get something like this. I'm going from -1 to 3. So I'm going to get -1 over 3 minus, careful here, this negative is from the function, right? This negative is, I'm doing f of the top minus f of the bottom, right? That's that negative. So then I get minus again from here, and then -1. This is a terrible thing here. So it's -1/3 minus, I think this is all going to become 1, because it'll be negative here and a negative here, so +1. So I think your final answer would be -4/3, right? Which is obviously wrong, because if you're going from here to here, whatever the area is, if it can be calculated, it definitely is positive, right? So this is a wrong answer. And the reason you got that wrong answer is because the fundamental theorem doesn't apply, because there was this vertical asymptote. Okay, the last thing we want to note in this lesson is that FTOC2, which was the theorem that said that this FTOC2 was the one that said the integral from A to B of little f of x dx is equal to big F, the antiderivative at B, minus big F, the antiderivative at A. So that theorem is also called the net change theorem when we just move this term to the other side by adding it, right? So I can write f of B is equal to f of A plus the integral from A to B of little f dx, right? So what are we saying? We're saying that the antiderivative y value, right, at B is equal to the antiderivative y value at A plus the net area under F, right? So in other words, say I have a position velocity problem, right? Then we know that the position is the antiderivative of the velocity, right? So that would be saying the position at B is equal to the position at A plus the area under the velocity graph, right? So we've seen this kind of thing before. We're going to use it a lot. It reinforces the idea that when you integrate a rate, then you get the accumulated change in the function. When you integrate the velocity, you get the accumulated change in the position function. So the integral is called an accumulator of change, and we're going to come back to this again and again and again. So this is just a brief, introduction to that, but don't worry if you don't understand that yet. It's going to come up again and again. Okay, what are our takeaways? A definite integral is a, pause the video and think, is it a number or a function? It is a number. When the upper limit of integration is a variable, then this integral is a function, right? So if you've got numbers on the bottom and the top, it's a number. But if we go putting a variable on the top, then it becomes a function, and it's an area function. The fundamental theorem says that this area function, where we have this number on the bottom and this x on the top, right, is the same as the antiderivative of f, right? So this is quite convenient that area and antiderivative both start with a, because you can just think really on top of little f. We usually call this big F on top of little f on the ladder, but we've just realized that big F is nothing other than the area function, okay? FTOC1 puts the result this way, that the derivative of the integral is equal to f of x, right? So that little f, that emphasizes that integration and differentiation are inverse operations. And FTOC2 puts it this way, the integral from a to b of little f is big F, the antiderivative at b, minus big F, the antiderivative at a, which is emphasizing that the area under the derivative graph, right, from a to b is equal to the change in y values on the antiderivative graph from a to b, okay? And the net change theorem puts it yet another way, saying that big F of b is equal to big F of a plus the integral from a to b of little f of t dt. So I hope you enjoyed that. It's a super important theorem, and we'll be spending a lot of time now unpacking that in different ways. Have an excellent rest of your day.